see you again here in Dresden. I hope it will not be the last time that you have the chance to visit us. I hope that at some point we can also come to Ukraine to have workshops within this frame of this project quantum materials. We have a lot of interesting talks, and I like very much that it's not only IHX, there's also IMW talks, and talks in the direction of thermoelectrics, which goes already beyond the things which we wrote up in our proposal. So, great. So I'm looking forward to a nice talk. And then I'll hand over to Sasha, who is the chairperson of this first.
No, thank you. Actually, the sound is okay, yeah, because I didn't ask people what they say. It is okay, because usually quite often there is a problem with sound. Because no, I mean they say they confirm it's okay. I can hear because I do not see here actually the online participant. But okay, I just wanted to say that it is my pleasure to be here again and in reality, yes, not online. And this workshop is devoted to the beginning of our project, which is GUKUMAT, German-Ukrainian Center for quantum materials research, right? And the idea of this project, which it is actually, who did not know, it was quite competitive projects, quite competition. It is BMBF project, and this is our project is among 4 projects in Ukraine, which won this competition. But the idea of this Center of Excellence is to make to make funding to fund this Center of Excellence, which accumulate joint research and attracts another cooperation. So it should be really core of excellence, and therefore it is the structure of this workshop. We planned first we want to discuss like internally what we are doing in open format, and maybe new ideas come, which materials we want to study, because the main actually idea about this work, it is theory assisted search for new quantum materials. It is from one side it is quite wide, could be a quite wide topic, but from another side, of course, we have certain materials which we are interested in, which we plan there, but also we plan to develop new collaborations, in new search for external funding and so on. And because of this, I'm especially, it's nice that here we have from point of Ukraine, it is not only Kyiv Academic University, but let's say the closest collaborator is the Institute of Metal Physics. And here we have at least 2 guests, let's say, from Institute of Metal Physics. It is Evgen Leny and Igor Sukhenko. They will present their parts of research, and also I'm glad and grateful that Institute of IMW, yeah, the institute which also interested in metallic research and in research of metal, will present, give some presentation, and I hope we will establish some new connections, because really I see that a lot of similarities in our topics and in equipment, which are similar. And but that will be tomorrow. And today the second session will be focused on theory. And this is also, I think, Alexei will present his idea how to develop this approach, which in the way of theory-assisted search, but and how to incorporate the machine learning algorithm. And the special guest will be Alexander Kordyuk. But okay, this is for the second part. And now I want to invite Volodymyr Bezguba. He will give a talk about, he is not the first time here, and he has experience to do experiments here, and especially important that he has papers which are hanging, hanging papers, which he should finish, and some ideas. They could be already some partly end, partly new, some results, and I hope he will try to start from this discussion.
Thank you. Thank you very much.
Sorry for the delay. Second time will be fast. I need to share it. Just people online can see it.
Good afternoon, everyone. It's a real pleasure, and I sincerely thank you for the invitation. I'm really glad to be here in Dresden. Thank you for the introduction from Alexander Kordyuk. Indeed, I will start with some continuation, and I'll remind you about an interesting material of iron, selenium, which is a very good candidate for topological surface states. I'll talk about that in more details in a second. Gukyumet's projects was mentioned, so I think I don't need to talk much about that. So yeah, why topological surface states are interesting at all? Quantum computing nowadays is quickly developing, and one of the biggest problems of how to make a quantum computer is the coherence time. And the coherence time right now is like microseconds still, and it doesn't allow you to have a lot of qubits in one computer to be aligned at the same time. So you can't run most of the algorithms which are required for solving the simplest tasks. There are some cases of software-related error correction, but overall, it's the most limiting factor. And for that, you need also like very cryogenic temperatures, like 15 millikelvins. And one of the potential solutions how to fix that is basically incorporating the built-in qubits, not in traditional way, but using, for example, Majorana-bound Majorana fermions, or in other words, Majorana-bound states, which basically requires new materials. And there are some attempts to do that with heterogenic structures, but one wants, of course, to have it like a material which has such properties. And recently, iron-based superconductors appear to be the class of materials which are very promising in that direction. Here on the slide, you can see all the main families of it. And today I will be talking only about iron selenium one. On the right, there are crystal electronic structures for all of them, and the feature which corresponds to the topological properties is this PZ band. I'll go back here because here it's bigger. So this PZ band, when it crosses the manifolds of DXZ, DYZ bands, it opens the gap in 3 classes out of 4. So potentially any of these 3 families of iron-based superconductors, they can carry topological surface states. So in case of iron selenium one, sorry. Yeah, I guess it's cut off a bit for some reason, but nothing much lost yet. Hopefully it doesn't happen on other slides. For iron selenium here on this DFT calculation, you can see the calculation without spin orbit coupling incorporated. So this PZ band with big circles, it's far away from DXZ DYZ, and when you so yeah, it's slightly sorry about this. Maybe I will open the PDF instead. Just a second.
It's the window from the left screen that's partially on the right. So yeah.
Yeah, I see.
Maybe.
No. Just go back.
I think
we just moved this
yeah.
one.
Okay, now.
Yeah, thank you. So this is with spin orbit coupling, and then PZ is quite far away and nothing interesting happens. But when you count in the spin orbit coupling and look closer at it, and not just at iron selenium, but at iron selenium, like half selenium, half tellurium, here opens the gap. And actually, like when you do the parity analysis, you see that there is actually inversion band inversion happening there. And in this, as a result of that, in this gap that opens, one should expect surface states appearing. Basically, a Dirac cone should be there. And this theoretical calculation-based paper, it was published in 2015. Since then, there were quite a few experimental attempts to study that. And of course, for such task, one can use ARPAS, which studies the electronic structure, the best method to study the electronic structure of the material. There is another approach to look at when you look at the material in the strong magnetic field, and then you check zero bias peaks. And there are papers which are signaling that by zero bias peaks, there are signs that it should be there should be topological topology there, not non-trivial topology. But still, these materials, iron-based superconductors, like you could have seen on these calculations, they have quite complex band structures. So a lot of things can be happening, and it's better to study in detail, like seeing what happens to each band. And one of the first groups who reported that was they published the result in this paper, and they were showing the Dirac cone at like it's quite well visible here and here. And they were reporting that these are the topological surface states, but the data was measured only with one laser energy, and their scenario, it was well studied, but only for one energy, and it was the starting point for us when we decided that we want also to revisit it, and we wanted to study it in more detail. So we performed such a study. We didn't have 7 EV laser. We used the 6 EV, but most importantly, we did detailed synchrotron study with different synchrotron energies. And first of all, you can see that gamma and Z points, they are well distinguished. So like we have good KZ resolution, and which means we can actually study that. And here just the quality of the spectrum that you can see, also the superconducting gap opening. This was a temperature, I don't remember, I think 2 Kelvin. And then here's some spectra at in between gamma and Z at 18 electron volts at temperature above TC, because we don't want gap to change the electronic structure for us. We want to see like how to see all the bands without the gap. And after taking also important notice on this, probably not that important right now, but just to mention, since I added it here, that it really matters how you study this, because if you, for example, use second derivative method, which is widely used for ARPAS, if you use it here for like derivative by momentum, then indeed it looks like a Dirac cone, but that's not correct, because like features are very distinguished in energy. You can see it on the original spectrum. And that's like you are supposed to be using second derivative by energy, so with which is the second picture. And indeed, you can distinguish very well like 1, 2nd, and 3rd features, which we at first like just identify. We don't map them directly what it is, either PZ or DXZ or DYZ. But later, by checking different energies one by one, and comparing it to different DFT calculations, we map what is happening. And another important note is that here there is a V-like feature, which reappeared in later papers by other people. And that's important thing, which indeed can be confused with surface state, with the direct cone, but there is slight distance here. And what's more important, if you have a surface state, it should be presented any KZ, because it's not bulk band, it's a surface band. But for us, it was not like that. And after mapping, after working with all that data, we made basically such map in, here you have quite an energy going like down to 20 milli electron volts, and this slightly dispersing band, which is DXZ, but PZ is just slightly diving below the Fermi level and then going back up. And due to matrix elements here, we don't even see it happening. So our end case scenario was that, unfortunately, what was expected in these calculations, again, it's calculations, it's not what you will see in real life, obviously. Like it won't be one-to-one. Renormalization is a factor. There is no strongly correlated theory like which can calculate all these things. But here one would expect that PZ will cross, sorry, not here. Here one could expect that PZ will cross DXZ DYZ very strongly, but from our data analysis, it appeared that it just barely touches, it doesn't even touch. So one would expect here a small gap. And then you also should encounter the renormalization. So it's sub-milli V size. And even if it's there, it's hard to detect experimentally. And more than that, we did scan the whole electronic structure over KZ, and we don't see any signs of that, any signs of surface states so far. But there is a new paper which was released in 2024. This was mostly just to remind you this story, or to those for whom this was new, just to show a brief picture. The paper from 2024, which was published, I think, just this June, there they, in a group of Shan, they also study the same exact content of doping with tellurium, 55% of tellurium. And they state that actually with a variety, in a wide range of photon energies, so over KZ, they can see Dirac cones, which correspond to the surface states. And therefore, they basically show very nicely that it looks like there is something. So let's talk in more details about it. On this spectra, you can see just on one example at 26 eV. But on this slide, I wanted to show a bit more. So like wide range, again, if we compare to what we did it to 50 electron volts, the ones which we like worked most of all. And okay, we don't look at this, we stop at 32 because 32 is what they are looking for. And indeed, these are original spectra, these are second derivative over energy. With laser, it's a very clear one. Again, V feature, which they call a surface state factor. We still think it's a V feature. So V feature appearing here, here, and then it's not everywhere that good. Like here, that it even might look like there is some gap between them, but it's consistent. But here again, something happens, like it's not very good. Here it's strong, and they stop. They don't go farther. In our case, data quality is slightly worse. Perhaps maybe we had a bit worse resolution, not by much, but it's comparable to theirs. And you also can see such V features, for example, at 20, at 21, 22. So there are these signs of some V features if you really like do a lot of data analysis so that you might extract something like that. So from the first look, it seems like not much new, except for they have it also over this whole range where we didn't see it. So it's unclear to us for now, like what it is. It's still an open question. It's still quite controversial. Like there are several different studies which keep on going, and it needs further studies. But let's go on. They do the detailed direct surface state peak analysis, and indeed, it on their spectra it looks nice because they show MDC at different binding energies. They indeed show that there are peaks arriving there. And when they studied the full width half maximum of those peaks, and the fit is also, at least on this particular one, on this spectra, the fit looks pretty good. But you can notice that when you plot the full width half maximum from binding energy, it varies a lot. Like here, it's the bottom is at 8 millieV. Here it's 6 millieV, so it's like goes over the place. But for that, actually, there is a good explanation because you need like to have like strongly very nice definition of where the Fermi level is and like where the leading edge is, and like all these slight fluctuations, they are incorporated basically in this error. So one can say that it's consistent when you incorporate also this error. And what's also very interesting about their work, besides the very strong result, if everything is correct, is that they performed a well-detailed study with different polarizations, not for all energies again, but they compare how matrix elements eat out from the spectra specific bands. And they explained it with tight binding model, and sorry, they explained it with tight binding model, and that these PZ matrix elements, they just add they band the bands a lot in this region for which we didn't have actually a good data, and which not good data, for which we didn't see this feature, and for which they don't continue with the spectrum. But also when you encounter like matrix elements, when you try to take that into consideration, they start from calculated band structure from DFT, and then you add renormalization. Again, when we did the study, we found some anisotropies there, but even the simple renormalization of a factor of in our study, we found it to be around 7 for specific for PZ, but here it's DZY 3. And when you count in for matrix elements, they also band it, and then like it aligns really well with experiment, but it's a lot of steps to reach that. It's not just renormalization, so it's a lot of assumptions in the process. And after that, it indeed looks like that in their scenario, which again, there are like, it contradicts our study. Like we simply don't see it. Like we would like to do similar analysis, but we just even if we can consider this V feature to be the topological surface state, it should continue like everywhere. Okay, let's keep bigger energies, but still it should be in this range, and it's not. It's just not there for us, and it was not just one spectrum. But still a lot of new data, a lot of new analysis, and what's the most interesting for me personally in this study is this approach, this attempt to incorporate to use the tight binding model and to use this matrix elements approximation to try and bend what you expect to get. But that was not all. In 2023, also there was another paper which they also say it was published in Chinese Physical Letters, and there they the authors claim that they make no, they make the assumption they state that the result is that actually there are topological surface states, but their data partly contradicts the data from a group of Shan, because they don't see, for example, on this spectra, you don't see any signs of V feature or topological surface states. And actually, when you check the DFT calculations and the ones with spin orbit coupling, you see that there is actually no crossing of PZ and DXZ. So they use different reasoning. Actually, their reasoning is based mostly on very limited data. So they speculate that in this area, the bands actually cross in a linear fashion. So that this linear part of dispersion, which is sort of on the margin of error, but it needs more study, I would say, but they, based on this, claim that there is actually, they see some surface states in their data. But it's just interesting that even those groups which agree on the theory that there is non-trivial topology in the material, they still contradict results of each other. So in short, to sum up this story, what it looks like at the moment, that from one point of view, not enough data is available, like it's not consistently studied. So one would expect that maybe after doing like a careful study in a wider range of photon energy on the synchrotron with both polarizations and hopefully at improving the resolution and using also FeSuma to try and be sure that you have the correct orientation with 100% certainty. Maybe that, not maybe, that will certainly help, and definitely more study is needed for this, because papers keep coming and contradicting results keep coming, even though the resolution keeps being good in these papers. So I think I will stop with that. Thank you for your attention. Please ask questions.
Thank you. Questions?
Okay, my first question, if it's not topological, as far as I understand, so we don't agree with these two papers that it's topological feature, right?
Yes, it contradicts the scenario that we got from data analysis.
That's in simple words, we don't think it was topological feature. Or do
I didn't mention the important factor that I'll return back to your question in a second, but important notice for this. This paper is actually called something like finely tunable material with Majorana states. So the idea is that, yes, you have tellurium 55%, and there is something very interesting happening there. That's for sure, like 100% certainty. But the question is, maybe it shouldn't be 55%. Maybe it should be like 52 or 60. Like there is it's highly tunable. You can like shift these bands slightly, and you can get some very interesting physics. But maybe that's also the difference in crystals that results in such results. So maybe it's on the margin on error, and actually it's not 55, but slightly off.
But just a question, as far as I understand, that you say it is bulk feature.
Yeah.
Yeah,
Yes, we say it is bulk feature.
Dimensional feature. They say it is surface state.
On our data, it's bulk feature.
I just want to ask then, what do you think is ZPCP show, and why do they see this in tunneling?
Zero bias peak?
Yeah.
Tunneling, zero bias peak in tunneling, it's so difficult question.
I'm not an expert in STM to talk in detail about that, but from what I know, it can be a sign of many things, and that's why I mentioned that. That's why I mentioned that iron-based superconductors is a complex structure to study. Like, it's not just cuprates. You have one band which crosses the Fermi level, and that's it. You have like 3 bands, potentially even like more, and hard to tell. Like, yes, it's interesting that there are these signs of zero bias peak. It certainly overlaps with the statement that from calculations from theory, it's expected that there should be band inversion there. But definitely in experiments something doesn't add up.
Yeah, for me it was actually I would better prefer that there are surface states there, just because you remember.
I would also better.
Strong,
yes,
I mean, strong dependence on temperature, strong dependence. This is a red-blue shift how this moves with temperature, and it moves with temperature in such a way that actually number of electrons changes, number of carriers. It seems that it changes. Surface area is changing. And my impression was I would expect that it is somehow redistributed between surface state and bulk state, maybe. But since you have shown there is no surface state, so maybe it worth to go more carefully on this, at least somehow to react on this paper by Shem.
Yeah, but doing experiments with a laser here, is there any plans to do that?
We were discussing that with Sergey, that we should try to get more data, more spectra. That hope. Theoretically, we should also see a very good feature like this. So yes, and we can do it with 6 and 6.5, I believe.
The question is only, do we have the samples for this?
So Sabina had the question.
I had a question, yes. So the samples are from the same source? I guess not.
You mean the samples over all these papers?
Yeah.
Of course, like pretty sure, yes. I don't think that group of Shan were using samples from IFW, because those were from IFW that we measured on.
Did you, or how were they prepared? You don't need to discuss this, but please check how they prepared it, because they are rather difficult to be grown and not from milk.
Yeah, a very valid and good comment, thank you. I was actually in this paper from 2023. They also tried, it's not on the top priority for what I was telling, but it's interesting that when they also tried to dope with iron, and I think they were discussing, like, I noticed that they were using some method which I didn't hear before about how to synthesize those. I can check on the paper after the talk. But they tried also like add iron, and it was making the situation worse. So like the gap was just right, and they didn't even cross. So it's actually bad for chasing the topological, so the surface states.
Maybe a follow-up, but there are many claims now that people say we now can control it. But I think it's a lot of claims, and it's really difficult to do.
One should just check. I'm not telling what this is.
No, I think that's also what check. Paka is doing and they have very nice results. They always have full control over the samples. But
it was just a rather simple question. The problem here, what I see from ARP, is that this inverted gap is very small.
It's sub
around
milli.
5 milli, and My simple question was, is there any ways to make it larger? Just to drop it with some.
It would be nice.
So you can just see the surface thing, because as you mentioned that you want to measure with higher photon energies, but I don't see how it's going to help, because you basically just lose the resolution.
I mean,
the lowest possible energies.
Just having a hope that
matrix elements.
So that they are not visible, but the surface is visible.
It might add some tiny bit of extra information, which might change like the understanding of it. But what I didn't mention enough during my talk, that intuitively for me, it seems like it's highly depends on the level of doping, and like it's very much of fine tuning how like you slightly change it, and because it's not very stoichiometric, you can't simply calculate like 55 to 45 easily. Yeah, like you would need like Oleg will tell about that later today. You will have a huge elementary cell, and it will take forever to calculate. So maybe it just this tiny fraction will change something, and that's what we see. Maybe.
Thank you.
Okay, thank you, Volodya. If you now move further, we will be in time, perfectly on time. So I would invite Sabina here, and I just want to say a couple of words about motivation. I see that the next two talks will be devoted to it's oxypnictide superconductor and then high temperature superconductor. And I actually it reminds me that I should thank Sylvia that she organized everything in so short time and all these talks. But we say that we are interested in theory-assisted search for new quantum materials. And both FeTeSe cuprates and iron-based superconductors, it is traditional, let's say, already not so new quantum materials. You see that there are some open questions remained, and actually I'm sure that a lot of open questions remain for cuprates. But cuprates, it is something already old. But what makes me very interested in this project here about cuprates, that one of the main question which remained for me 20 or 15 years ago, how the spectral weight redistributes with temperature. Because when gaps open and when pseudo gap is opening and then superconducting gap is opening, we see that there is a strange redistribution of the spectral weight. If stay at antinodal region, you see that when pseudo gap opening, the spectral weight is gone somewhere, and then it appears back when it became superconductor. And the question where it goes, to address this question, you need to measure with ARPAS, you need to measure Fermi surfaces for each temperature. With normal ARPAS equipment, you should, let's say, approximately 1 hour spent to measure the Fermi surface map. To cover all the Fermi surface, and you need to make it for each temperature, and this temperature you need to stay at one point, and you also would be nice to make it also for different excitation energy because of matrix elements. And now with FeSuma we have its very fast system which allows you just to measure very quickly in terms of, let's say, 5-10 minutes to measure this Fermi surface map at one temperature. And this is important to measure. I think we can now measure this redistribution and to understand how it goes. Therefore, I would be I would like to go to cuprates, and therefore we are interested how we can synthesize now, because cuprates, if before we had a lot of samples from different sources, it's interesting how it's possible to do in IFW and how it's possible to do in Ukraine. And actually the same is for iron-based superconductors. Therefore, please, I would be interested very much.
They will record the talk, or do you rather not? They will record the talk.
Oh, I don't like that. Yeah, actually, thanks for the introduction, and also thanks for the invitation.